Well, here we are at the last chapter, chapter 22, part 1. From chapter 22, we will only be doing the chi-square goodness of fit test. So it will actually be a relatively short chapter, but an important one. This is the one and only non-parametric procedure you're going to learn for a test of significance. The goodness of fit test, rather than being interested in testing a claim regarding a particular parameter, as we've learned in past chapters, such as the mean or proportion, we're interested in testing a claim regarding the entire population's distribution. So let's take a look at this. If we roll a die 600 times, does the set count differ significantly from the expected values that we should get? In other words, if I roll a die 600 times, I would expect by the laws of probability that I should see a 1 come up about 100 times, 2 come up 100 times, 3 100, 4 100, 5 100, and 6 100, correct? Because they all have a 1 in 6 chance of occurring. So 1 in 6 times 600 gives me my expected number. But let's say that you rolled a die 600 times and you got these actual numbers here in this row. Does that mean that the die is not fair? Does that somehow show that the die is loaded? This is how we can test it. We do a goodness of fit test. Here's another problem. We're told that 40% of new cars that are sold, they're white, and 45% are black, and 15% are red. If we take a random sample of 100 cars, does our actual counts really differ significantly from what we expected? So we would expect to get 40 new cars that are white, 45 that are black, and 15 are red. But we'll do an actual count, and we would see, is there some difference from what the stated breakdown of the population is? How do we do this? How do we test it? How do we give it a quantitative value saying, yeah, I think the dice is loaded, or that particular plant isn't producing that percentage of white cars, or whatever, is we do this goodness of fit test. It's a procedure used in differential statistics to test claims regarding that entire probability distribution. Goodness of fit tests apply to experiments that consist of a series of n independent trials, that's simple random samples of size n. The qualitative outcome of each of these trials can be classified into one of more than 2 categories. In other words, you have to have 3 or more. Otherwise, you're just into a 2-sample problem. So we let P1, like 2-sample proportion problem, so we have to have more than 3 categories, or more than 2 categories. So we let P1, P2, all the way up to Pk be the claimed probabilities for the K categories. Compare observed frequencies and expected frequencies. If they differ significantly, then we have evidence against the claimed probabilities. So just like I showed you in that slide earlier, the expected number of rolls, times that I would roll a 1, if I rolled a die 600 times, should be 100. Does that being 90, the actual value 90, different from 100, is that significant? Is the 105 from 100 significant, and 115 from 100, and so forth? This is what this test will tell us with a quantitative number. So here's our little guideline, our little setup. We set up the hypothesis to be tested, decide on a level of significance depending on the seriousness of making a type 1 error. We find the value of the test statistic. The way we do that is we have to calculate the number of occurrences to be expected in each of the categories if the null hypothesis were true, calculate the number of occurrences that were actually observed in each of the samples, compare the observed number to the expected number using a test statistic. So after we do that comparison, we'll get a test. Number 4, after we find our test statistic, we have to use technology to find the p-value. Reach a reject or do not reject decision by comparing that p-value to our level of significance. And then state the decision in terms of the problem, your conclusion. So let's see how all this is done. Well, we'll state our null hypothesis. The random variable follows the claimed distribution. That is, these proportions are true, whatever they might be. And the alternative is that the random variable doesn't follow the claimed distribution, and all you need is one of those proportions to be different than what is stated in H0, and you're going to reject that null hypothesis. So these hypotheses deal with categories at the same deal with all the categories at the same time, not just one. So we have to find the expected number of things, and this is how you would find it. You have your sample size, and the way you find the expected value in your first category is n times the proportion of 1. Your expected value for the second category is n times your proportion for that second category, and so forth. That's how you would find the expected numbers. Now, of course, the observed is you just look at what you observed. We use those to find our test statistic, and this is our test statistic. We have this thing called chi-squared. It looks like an x squared. That's what the distributions are called, the chi-squared distribution. Our test statistic, that's why you see the knot. This is our test statistic. And what it equals is you're going to sum up for each of the categories the observed value minus the expected value in that particular category. You square that number and you divide by the expected value. And you sum them up for all of the different categories. Now, I know you're looking at this and going, what is she doing all these different numbers and letters? But I promise you this test is very easy. What it is once I get all this background stuff done and we do a problem, you'll see that it's actually quite easy to do. So just hold on to your hats. It's not as bad as it looks. So even before we can do this, we have to make sure that certain conditions are met. So the test statistic is approximately a chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories. So all expected frequencies should be at least 1. That is that all the expected values have to be greater than or equal to 1. And no more than 20% of the EI should be less than 5. So let's go to our problem of the fair die. We roll this die 600 times. Remember that the probability of getting a 1 is 1 in 6. The probability of getting a 2 is 1 in 6. So our null hypothesis would say that the probability of getting a 1, 2, 3, 4, 5, or 6, they're all equal to 1 out of 6. The alternative says that at least one of those is different from 6, from 1 6. That's what we're testing. Is this dice fair? So remember, we get our expected value to p times n. If n is 600 and p is 1 6, that means my expected value is 100. And it would be 100 for each of the 6 different categories. So my actual numbers that was given. To find my test statistic, I need to get the quantity. The actual number minus the expected number, I square that value divided by the expected number. So let's look at the first category. I would take 90 minus 100. That's 10. I square that. That's 100. And divide by 100. That's how come you got a 1. I take 105 minus 100. That gives me 5. I square that. That's 25. I divide that by 100. I get 0.25. And so forth. That's where these numbers come from. The 1, the 0.25, the 2.25, the 0.25, the 0.25, and the 0. Now to find my test statistic, that means I have to add up that last row. And I get 4. You need to find the p-value, but you can't find that you can only capture it like in the t. So we've got Minitab that can help us find the p-value, and this is how you do it. Since we have our test statistic was 4, we want to do the cumulative distribution function of 4, and we're going to put our answer into K1. We're going to tell Minitab I want to do the chi-square distribution, where I have 5 degrees of freedom, because we have 6 categories, so the degrees of freedom would be 6 minus 1, 5. Now when we got that K1, the way that these work is it's in the right tail, so we have to do the complement, so we have to say let K2 equal 1 minus K1, then print K2, and that will be our p-value. Now if you don't understand all that, don't mind, you can copy and paste this to get your p-values, but on tests and stuff we'll give you these p-values. So since the p-value, it ends up being 0.55. If you look, K2 is 0.549416. You round it to the second decimal place, it's 0.55. Since it's greater than the significance level we stated at the beginning of the problem, which was 0.05, we do not reject the null hypothesis because that p-value is large. So there's insufficient evidence to reject the belief that the die is fair. We're going to continue with some more examples in Part 2.